Today we are implementing Lean. In Lean, we are going to be
You're
implementing
sure the mic is on?
the Hyperreals. Yes. Now the mic is on. Okay.
Actuate it.
Tell us about the Hyperreals, maybe in a more
Okay.
concise way this time.
Yeah. Here, help me out then. Prompt me with a couple of questions.
All right. So when I was learning about a little bit of physics recently, they kept talking about this thing like compact spaces and how compact spaces are different to a normal space somehow. And you just mentioned compact spaces when you're describing hyperreals. So like what is the point of a hyperreal versus a real number?
That's a good question, but the answer for that one is going to reach fairly deep. So maybe a different place is a better facet to start at. We can dig all the way into that, but it's going to be a really deep tunnel, even deeper than the previous one.
Let me show a picture here on Google, which is I think the one you showed me last time, where it's just basically multiple little like graphs like going one from the other. So you start off with like a number line, and then the number line's got fractions, and the fractions go into like more fractions. But there was a nice one where went like 3 levels down, 3 or 4 levels down.
Can the people on YouTube see whatever you're putting? Because I can't.
Yeah. And share.
Okay, well, that's good enough.
Let me share on Discord so you can also see whatever I'm doing on my screen.
Can't you just share your screen at the same time and like hook it up to OBS?
Oh, maybe.
Or is that like whatever? Another time.
Okay, so hyperreal numbers. So yeah, it's something similar to this. That was like quite a cool image. I don't know where you shared it with me last time, but the idea is that you've got normal numbers, and then the normal numbers. Oh, they go in both directions. This one. So you have.
Let's call them standard numbers to line up the terminology a bit, which will be helpful later.
So you have standard numbers, and then the graph I saw is where basically like things kept getting smaller, but this one says they can go bigger as well, which I don't realize it can go both ways. Infinitesimals and infinite. Makes sense.
It's actually easier to start just with infinite numbers because you don't need the whole reals or hyperreals to define them. You can start with just the natural numbers and then construct the hypernatural numbers, which look like the ordinary natural numbers, except beyond them there's an infinite segment. If you look up hypernatural numbers, they might be able to see one. But it would look like, if you've got a pen next to you, try drawing those. Put a vertical line to mark a tick on a line perpendicular to it and set that to be 0. So the left edge. And then you draw an arrow going right because there's no biggest standard number because you can always add 1, 6, 7, 8, so on.
Okay, hold on. Let me try to draw this. Okay, so I've got a line. And now, what do I do with the line?
Okay, now move your pen to the right without continuing the drawing and draw a 2-sided line and put a tick in the middle of it and mark it as H or omega if you prefer.
Okay, I need a straighter line. A tick in the middle. Okay, here. So this is H.
Yeah, and make sure that from H, well, on the left there's H minus 1, H minus 2, and so on. And on the right, H plus 1, H plus 2, and so on. There's no biggest infinite number, but there's also no smallest infinite number. And that's where interesting stuff that's like is exploitable happens. Like you've noticed in the diagram that there's 2 arrows pointing at each other in arbitrarily large standard numbers into natural numbers in this case, and arbitrarily small but still infinite numbers, the left of the 2-sided arrow. And
to this one that I like. Yeah, this, yeah.
They're connected to each other, but you can never find a single point of connection. And this paradoxical nature of it is actually very useful because it allows you to use these infinitely large natural numbers. One to just represent like some big quantity. Take computer graphics. What usually there's some global constant or a constant you can pass for the number of triangles in some mesh, essentially the resolution. In this case, expressed not as the scale length, but the number of pieces. So it's an integer. And through the hyperreals, just like how numbers idealize the real world, this idealizes the idea of big and small quantities. Despite the numbers being infinite, they have plenty of uses for ordinary finite applications. And treating things as infinite or infinitely small is very common. That's how, what's his name?
Oh, here's the picture.
Eratosthenes measured how big the Earth's circumference was. He assumed the sun was infinitely far away, which is wrong, but the error it incurs is very small.
Interesting.
Like, I think there are more orders of magnitude between, like, you and the scale of the Milky Way galaxy than between you and a single atom inside you.
Fascinating. Does that mean that the black hole?
So, like, compared to the galaxy, modeling you as being infinitesimal is totally legit. In fact, modeling the entire Earth.
That's funny. So this is the graph that I was thinking about when you first told me about the hyperreals, which is actually the surreal numbers. It just like helped me think about it more clearly. But is there a fundamental? Is there like a big difference between that hyperreal and surreal?
That one gets subtle. The upshot is it depends on the axiom system you use, but under many, the two are actually isomorphic. And you can think of the hyperreal numbers as the largest set size sub. I don't want to say set because it's not. Yeah, it's actually a subset of the surreal numbers, which are too big to be a set. So when you want to cut something down to being set size, you end up with the hyperreal numbers anyway. In practice, you can just like what's really beneficial is having arithmetic and ordering for infinite and infinitely small numbers. And so freely identifying the two in practice works out like okay. There are more subtleties to that, but I expect the kind of person to care to be the kind of person who's obsessed with subtleties anyway.
Okay. So these this surreal numbers here, it's got this like little W. What is that character?
Omega. It represents the simplest infinite number, natural number, and infinite natural number. Because it's not the smallest, because there is no smallest.
So
Omega minus 1 is still infinite. Omega minus a trillion is still infinite, and it's smaller than omega by exactly a trillion, in fact.
So then those
is that like the expression you can write omega is the simplest way to express some infinite number by just writing down a symbol for it. And like omega plus 1 is you could give it another symbol like I don't know, omega prime, but these two symbols are related, and so one of them is kind of redundant.
Okay.
And the simplest one, yeah.
Then the other symbol, if you go infinitesimal, what's that symbol? Where like it's a sideways.
Usually
omega.
It's an epsilon. It's the Greek letter E, and I think it was first used by Euler to express E for error.
That kind of makes sense.
Because you think of it as the error in some approximation.
Oh, here's a pretty cool picture about this. Interesting. Surreal numbers. Okay, so let's get coding then. Where do we need to start here? Have you got a link from your live share, from your live session?
Yeah, I'll send you a link. Oh, I'm in Cursor, so I need to quit out of it and open VS Code. You have to pay up for it, but I really do like Cursor.
There's a number file video about it. Seems. Oh, it's an article.
It's giving me some saved things, so hang on.
So what got you into Hyperreals? Why is this captivating your attention right now?
Thinking about scaling, especially from ML, this just gives like a principled way to be able to even talk about scales, because you can say that one number is bigger than another in a sort of permanent sense. Because, like, say you, okay, like some problem across 3 scales. Say one scale is supposed to represent like the scale of 1 meter, like a physical problem, something on the scale of a human body, roughly.
Yeah.
Then you can have a scale that's, I don't know how many orders of magnitude smaller, but enough that you can pretend it's infinity, say 15 orders of magnitude at the scale of like an atom, or maybe a few less than that, to get the scales of atoms and molecules. And then another scale for the Earth. You'd pretend that the Earth is infinitely bigger than you, because the approximation works decently well. And how you can actually work with this in practice is you have all these symbolic expressions in epsilon and h, or in some infinitely big and small number, and then you can do a bunch of simplification with them. Then at the very end, just plug in a big number.
I see.
Which is what most symbolic engines do anyway for evaluations of this kind, where you have some symbolic parameter.
Okay, that makes sense. So, in other words, there's many things in ML where you're talking about like
why does it captivate my attention completely would be hard to say, because it's just in like so many little ways. They just suggest themselves as a good way to think of things, and I've yet to find them unhelpful for thinking about something that can be thought about mathematically at all, which is like damn near anything.
So it's basically a way to deal with scale, so that you can create mathematical formalisms beyond the countable set. It's almost like your computer has computational limitations, and
instead
of saying like how many gigabytes, like instead of saying how much time X amount of gigabytes will be able to complete a task on your computer, you almost talk about like how many computers there are, like at a different like level. And then the next level will be like, okay, well, how much compute do we have on Earth? And then you multiply that by the planets like that have compute. And then it's like, okay, well then, and then you go down by saying like, how many electrons do you need to calculate 1 byte or 1 tensorflop or whatever. So it's basically like ways to reason about things at scales that become uncountable.
Yeah, to do accounting. It also just leads to a different way of thinking about math as a whole, to the point that one researcher in it, he's dead now, sadly, he died in 2012, Edward Nelson. He was a mathematician at Princeton who came up with radically elementary mathematics. And like a lot of math things, the name is pretty carefully picked. Well, the mathematics, obviously. Elementary because John Stillwell was probably the best known mathematical historian alive. He came up with a definition of elementary math, which doesn't use infinity. So finitary math, combinatorics, finite combinatorics. But calculus is not elementary because it inherently uses some sort of infinity.
Oh, just approve me there? I'm trying to join in now.
Oh.
I'm signing as anonymous guest because I don't want to put in my password for GitHub right now. Okay. Oh, this is. Oh, you put some work into this already. Okay, can you run us through the code here from the top and let's see if we can get a grasp of this?
Or you can see the line 4's import standard, for example, right?
Yeah. I'm following your cursor, so you can just go around.
Okay, cool. The import MathLib algebra is because MathLib has a definition of the mathematical structure of a field, which happens to carry all the basic arithmetic operations. So by implementing that, I should get a decent amount of functionality. The next block of code is defining how to print various things, or in the case of rationals, how to hash them. Rat is well, you can actually see how it's defined in the standard library. You can ignore the bit on line 19 with the MK, but I think num is really not a good name. I can see why they wouldn't want to say numerator and denominator, especially as mathematicians, but this is just a little too short. The den and z and reduced are proofs that these carry around that these are legitimate rational numbers. Line 25 as well, that the denominator is not 0 because that's not a legit number. Not as how they define it anyway. But they implement a bunch of type classes, but they didn't implement hashable. But it turns out it can be derived, so good enough for me.
Okay.
I also defined how do you hash a single character, or rather, I got this from. Oh, actually, it says where I got it from.
So what
Yeah, if you're ever stuck in Lean for like more than 20 minutes, asking on Zulip is probably a good idea.
That's a good rule of thumb for sure. So what does hashable do for the hyperreals? Why is this important?
This is for implementing it. And the core backing data structure, there's dense representation and sparse ones. Basically array or hash map. I'm just going to use a hash map where the keys are a power and the values are, well, the value of a coefficient, in this case, rational numbers. I just picked rat instead of float because they have decidable equality and I didn't want to deal with like niggling floating point issues. But hyperrational numbers work, and this works over any field, which the rationals already are.
Okay.
So that's more of a technical implementation detail, not significant to the greater thing.
Okay.
Line 13 defines how do you print a hash set, which is not fully satisfying, but it'll do.
Alright.
That's some dead code. And this is how to print reppers. Well, like how do you print a hash map?
Yeah.
And you can see the test. I want to define these syntactic sugars to define tree map. Red, black tree. Just like how there's the hash syntax for arrays.
What's a literal?
Eval is basically like print. Yeah.
So what would be a literal in this case?
Actually, we implement literal syntax for hash maps. Not, I mean, it could be cleared from a literal, but that's not the part that I mean. There. Like on Python, using the curlies will by default create a dictionary or a set.
That makes sense.
Yeah. Just a more convenient syntax. Dictionaries are important enough and Lean's extensible enough. And this can just be taken probably unhealthily far. Like writing T or tree in this, that's one thing. But I can easily see this getting abused to hell. Okay, a bunch of emails. No idea if this derived hash is even that good. It seems to just be the ASCII code, but it'll do. I'm going to do some. A class of I don't have a good name for this. The idea is to define a type class that, given a type, maybe a structure that will create like the hyper version of that type. I decided that starting with that was too generic and to just literally stick to hyperinteger as well. I upgraded that to hyperrationals because I wanted to be able to divide.
Okay.
Oh yeah, the coefficients are represented rationals from or to exponent with implicit variable h meant to represent a hypernatural number.
So if we're gonna use this for ML, does it make sense to connect this to like matrices and linear algebra and that kind of stuff? Like eventually like tensors and whatever?
Oh yeah, at some point. The representation of this is basically going to be something like a polynomial and therefore under the hood an array.
Okay.
Which works decently well. Like certainly this implementation is far from the most efficient, but that's not the concern yet. It's more what I want to be able to express with it.
Okay.
Oh, here's something you can do with the hyperreals that would otherwise take like 10 years of learning math. You can take the derivative of a function that's discontinuous at the discontinuity. Like you can show them the step function, a function that's 0 on the negatives, 1 on the positives, and then at 0 can be whatever. But the point is that it has a jump discontinuity. You can approximate it with a smooth hyper real function that cannot be expressed in standard mathematics, not directly anyway.
Interesting.
Like you can express it by an encoding, but the encoding is basically equivalent to doing the hyperreals. So you haven't, that's just like an uglier way to do the same thing.
Huh.
At that point, you're really just contorting yourself to not have to learn something new.
Interesting. Okay, well, that's an interesting use case there. And then maybe we can talk about what is the lack in Lean at the moment. What is the issue? So you said there was a representation of hyperreals, but it's not fully implemented, or what is the current situation there?
That's purely for theorem proving, and that it's fundamentally non-constructive. Like if you go to Moogle and you just type hyperreal, Moogle.ai. Like I'm looking it up right now. It'll probably be a non-computable def.
Hyperreal.
Okay, this one is not non-computable, but it gets non-computable pretty quickly. One of the things that have turned people off from the hyperreals is that, for example, in generality, even adding them together can be undecidable because you could end up with some expression, say h, well, even h plus k, but k could be negative infinite, and then even the sign of h and k might just be unknowable or take an infinite amount of time to compute. But this is not something that shows up in practice. What the hyperreals used in practice look like is very much like how engineers and physicists use numbers, except now they're 100% legit mathematical arguments, and people don't have to put everything in quotes around infinite decimal or hedge so much. But it also gives proper guardrails for what the rules actually are. That was why when you were writing 100 with a dot dot dot, or you had that picture, I was so insistent there must be a 0 at the end of it.
Okay.
Okay. If you go to Mathlib 4, wait, I can send you the link now.
So there's
DMD.
So there's hyperreal under data.
Yeah.
And then real.
But even this, I remember this was an even simpler problem in Lean. I think in Lean, polynomials are not computable. That they were, for Mathlib, defined as like a purely abstract interface, which is very generic, but it's like a bit too generic for like actual coding.
Send that link to me on the chat here or in Pasta.
Sure.
Hyperreal numbers on the ultra filter extending the co-finite filter.
We're not going to talk about filters today. Not important for now.
Deriving inhabited. Align Hyperreal to Hyperreal. Then you create a namespace for Hyperreal.
I think the align is in the transition from MATLAB 3 to 4, where they changed the conventions. For one thing, they went from lowercase to upper.
Interesting. Okay, so this is the whole. Okay. Okay, so what's short of this implementation? Why do we need to?
Let's see. We should start by going to filter. Where is filter? Mathlib.order filter.
Seems like there's a
especially the cofinite filter.
Let's see if we've got any chats. No chats. Testing the sound. Sound still seems good. Okay, cool.
Posted in Zulip. I really want to look at is not this, even the polynomials, of which there are a lot of them. Oh. Okay, there. Look at this. Here.
Okay.
Notice the line 56, non-computable section.
Yeah.
Everything in that scope is marked as not computable.
So you can't do what with it when it's non-computable?
You can't like actually construct values. It doesn't generate actual code to generate actual values at runtime.
I get it.
You can still type check, which is very powerful, but that's purely a compile time, which isn't much use to me though.
I see. So you're looking to actually be able to compute things.
Compute with it. That's why I was interested in talking to Thomas Scrivan and looking into Silene, since it's trying to be NumPy for Lean, among other things.
Wow.
I think Lean will have better odds, though, with having good bindings. Well, let's see what's out now. PyTorch, the new Apple one, which I personally like, MLX, TensorFlow. Oh, and of course, JAX.
Lean or
considering Silene taking inspiration from.
Oh, Silene.
Yeah.
No, that's not it. No, not finding that. All right. Let's go back to the code here.
Okay. I'm on line 10 and where okay, I'm moving cursor back down to like line 50. I don't need the to do because the interface thing does it for me. So I just define an add function between, well, if you look at line 51, do you see like a sort of bluish thing that says coefs printed on it, or do you see nothing?
What, the blue squiggles under coefs?
Yeah, like with the maps to symbol.
Yes.
Okay, good.
Maps to is like an arrow pointing to the right.
Yeah.
Yeah.
Written out, and this is a proper repper of this would print it like this. That would represent 2 times h, because the coefficient is 2 and the power or the exponent is 1, and because everything is with reference to h after the whole mini rant about why to start with the hypernaturals rather than the full hyperreals.
Okay.
So this is actually an infinite number. The zero coef is in particular important. We're splitting them by positive, negative, and 0 degree. Mm-hmm. I derive another thing for rand because it didn't have it already. A bunch of prints. Mm. Currently defined comparable rational. But I can just write Q. This is always something I think about when using vocabulary, where like I figure, oh, they probably know Q, but this attitude is exactly how confusing notation proliferates. Anyway, though.
It seems to be a specifically worse problem with mathematicians for some reason. I don't know, something about the way they think. They kind of like maybe think that everyone knows what they know or something.
I think it's because math has probably the deepest concept tree, which is also why there's the kind of obvious thing people notice. So obvious that at some point people like act as if it's false, which is that math is hard and that it builds on itself. And if you miss something or don't get it, you can just be totally blocked on a problem. In fact, people are totally blocked on problems. Probably the oldest open problem I know is whether there are odd perfect numbers. It's been open since Euclid at least, so like 2,300 years, 2,400 years and counting.
What's a perfect number?
A natural number is perfect if it's equal to the sum of its divisors except itself. So 6 is perfect because 1, 2, and 3 and 6 divide it. 1 plus 2 plus 3 is 6. 28 is also perfect. And you should do that one aloud for everyone's benefit, as should anyone watching.
28.
Show that 28 is perfect.
What's after 28?
It grows pretty quickly. It's like somewhere between 4 and 600, I think. The next one's way bigger. It's not even known if there are infinitely many, though people think there are. And people strongly suspect there are no odd ones, but there is no proof of this.
Oh, it just needs to be an odd number. Oh. Is equal to the sum of its divisors. Proper divisors. Sum of its proper divisors. Okay. Interesting.
I'm glad I learned the merge with function. Very handy. I don't have to write those.
So now we do need. So now we are using fields, but we're not using a hyperfield.
Yeah, hyperfield is not the standard term. I just couldn't think of a word for it. Like the hyperreals are a field because they have plus, minus, times, and division defined everywhere, and they all work like an ordinary arithmetic. All right, of course, the declaration uses sorry. The multiplication is just done the naive way with some nested loops. This could be done faster with convolution and a fast Fourier transform. Not now. And these are various proofs, all of which I've ignored.
Okay, so the idea is
Some of them could probably be filled in with various proof techniques, but I don't actually care about proving anything. I just wanted to find the basic operations, such as inverse and then division.
So is the idea that all of these would need to have proofs fleshed out for each of them, and that would end up looking something like what's in MATLAB right now?
Yeah, that each of these is some proposition, and therefore to construct a value, you have to give a proof. Like, this is the difference between, like, you know how Boolean numbers seem to be used in two ways in math that are definitely related, but not exactly the same. And what I mean is, one is using them to just define what a set even is. You say, that, like, when you write that set builder notation, like, look at line 95. Where P maps, I don't know, into the Booleans. So, like a filter, wherever this proposition is true. The difference is in. Yeah. Okay.
Okay, sorry, say that again.
All right. The difference between a proposition and a Boolean mostly can be wrapped up by what happens at false, where like a false Boolean is just another value, like true, a 0 instead of a 1. But a false proposition, that corresponds to an empty one because it's a proposition that can't be proved because it's false, and therefore there is no way to fill out that entry. So an empty type. The difference is that in propositions, you can't just produce true and false values. The proofs are essentially what lets you do that by showing something to be true or not.
Okay.
And the other Booleans are, but the Booleans by themselves are, well, it's a two-element set with some operations. So they're playing double duty. And you can use something else to represent the type of propositions, and that's how you get homotopy type theory and things, but not today.
Yeah, homotopy type theory is pretty cool. Yeah, we had Urs Schreiber explain to us like from scratch, like the concept behind it, and so cool because it starts off very pragmatic, where he's basically saying like think of it in very realistic terms or practical terms, where you basically have this thing that measures these probes that like literally go out and like actually measure like a space. So you have to think of it like literally like maybe little satellites that are going around and surrounding a planet or something like that. And then those coordinates of those probes like basically give you this sheath. It's like a shape. And then from that you can like do a whole bunch of maths because you've got these numbers based on these like probes that have measured things. And I was like, oh, that makes so much sense. and then 20 minutes later it gets so deep
Yeah.
that it's like you quickly lose the imagery of these little satellites probing a planet.
I really wish there were more diagrams in the N lab. Did he record the lecture?
Yes, yeah, it's there. It's really
Was
good.
it for Topos or for Wolfram? Oh, for Wolfram.
Yeah, it was like 3 hours.
Did you
It's
get
like
your question in?
no. I didn't dare. There was some. Yeah, it was pretty intimidating. I'm not gonna lie. A few people got some interesting questions in, but he just went straight for like nearly 3 hours, like just full on. It was impressive on like multiple fronts, and like one of the things that was impressive is like it seemed like he hadn't slept for like 2 days, and he just got off a flight like to another country, and then he did a 3 hour lecture with us. I was like, damn, this guy's impressive, man. Apparently his work ethic is ridiculous. Like his output is like unparalleled.
Is what is unparalleled?
His output, his like
Uh,
productivity. Yeah.
Shout out to Schreiber. Now the whole stream knows you well.
um,
Here, let's define inv. This is where I expect complications to really start showing up. Is just thinking through inverses. They're not dot comment. Guess not. Okay. Look at line AD. So thinking of this expression's inverse. To the minus. You see that? So the line. Also, you can write on it. You don't have to just follow. You can type stuff. The multiplicative inverse of 1 minus h, where h is unlimited. Well, that's some big negative infinite number.
okay. Let me see what I can figure out here. Your implementation of the mole method for the Levi-Civita structure in Lean seems generally on the right track. You're correctly implementing the pairwise product of the coefficients from the Levi-Civita instances, combining the powers and multiplying the coefficients. However, there are some aspects that need attention. Accumulating coefficients. When you have multiple pairs of powers whose sum is the same, you should accumulate their coefficients. Your current implementation might overwrite coefficients with the same power rather than adding them together. Does that make sense?
Yeah.
What? Your current
Wait, no, that's still right though. Like, what if I do like say just h squared times h squared? So I should get h to the fourth. The power and the coefficients for both will be a 2 and 1. So I get power prime would be equal to 4, which is right. And the coefficients would be 1, which is also right. Should be inserted at every. Yeah, it should be.
So what's out here? Oh, this is the variable out, okay. So is it accumulating the coefficients? How do we test this? You mentioned that we need to implement that we might want to try to do some
Right.
tests, right?
For testing this one, some unit tests. Eval has basically been playing that role. I don't know if eval even works on that line. I guess the eval has to be outside the block definitions, like here. I think there are issues in the multiplication. Argument, standard map, not insert. Oh wait, maybe this is not the issue.
So it says to write tests, you would create a few Levi-Civita instances with known coefficients, multiplying them, and then verifying the results match expected values.
Every time you see standard.hashmap, replace it with lean.hashmap. Oh, I guess that was all of them. Now what's the problem with it?
Okay, where should I put these tests? Should I put them right at the bottom?
Yeah, just near the code. There. At least addition seems to work. Okay, this looks wrong. Actually, that's right. Because this is 2h times 2h. That should be. Thanks.
Unique powers. It says we should test for unique cases like multiplying by the 0 or one element of a Levi-Civita.
I think I actually did that earlier, so let's put that back.
I've got some test code here for us. I'll just make some last tests here.
Yeah, perfect. Yeah, good idea. Putting in some constants. Maybe call them something other than prime after them, A, B, C. Just because A is often used as an implicit type variable in generic code. Does that actually matter in this case, though? Only if a generic one is defined later.
Shouldn't we put these tests in a separate file, actually?
Not yet.
Not yet, okay.
Because you have to define stuff before it's used in Lean, like in a lot of theorem provers, because the syntax parsing is so expressive. Unlike in most modern languages where you can order functions pretty freely, because everything just goes through the main function. But that's because their syntax is more regular.
How do you make...
Oh, it's not called like that. You don't say dot mul. Like, look here. This doesn't If you want to call it like that, you would have to call it like field. Look at line 67.
Got it, yeah.
Like field.mol, well, 1 and 2, just like the ordinary numbers.
Okay.
It's not like 1.mol. You,
Yeah.
but it does allow you to write this.
It's a binary
Which is
operation
better.
with two.
Yeah. Yeah, Lean has type classes for every operation, and by overloading them, in the case of field, it extends add, sub, div times maybe even power.
Okay, I'll go back and fix those. I just want to first get everything down.
Yeah. Inv is the big one. Once inv is defined, in fact.
What's ind?
Inverse, multiplicative inverse, one reciprocal.
How much do you understand about homotopy type theory?
Comprehensively little. Snippets of it and many pieces of the math in it. I don't know, a decent amount at this point. I'm not a homotopy theorist, but I have some idea of the importance of homotopies. Through thinking about infinitesimals, actually, it puts you along kind of a similar course.
Okay.
And its close links to model theory. Well, model theory is not so far from type theory.
Okay.
In homotopy type theory, mostly I see why, like what's beautiful about it, and also the actual implementation of it. The core idea is a very simple one of replacing a sub-object classifier instead of the Booleans to say, instead of the numbers 0 and 1, the numbers 0, 2, 1, a whole interval to express like degrees of confidence. This is conflating some things, though. This is not really specific to the homotopy part.
Yeah, because he didn't talk about that. I mean, basically the main thing I got from it was ways of connecting disparate mathematics used for various aspects of physics specifically, and saying like these things actually have links, so we can bring all these different things together.
Yeah. Even before that, if you look up Computational Trinitarianism by Roberts or Bob Harper, it's on the MLab, where you'll find an interpretation of stuff in category theory, type theory, and I think the third one was homotopy theory. It's a table of correspondences. I don't think it's fully filled out because it's still current research, but it's far from empty. Let's ask Wolfram Alpha what the multiplicative identity is.
Programs as proofs, relation between type theory and category theory. It's like equivalences. So in intuitionist logic and type theory, a proof of a proposition or a term of some type. In programming languages and computation, a program or a lambda term with output of some data type. In category theory and topos theory, a generalized element of an object. So it says that those following notions are equivalent. All those things are equivalent. A proof of a proposition, same type, or term of some type, a term of a type. Program with a data type, a generalized element of an object.
Gotta be careful, Dan Lab. Too many links and you'll be lost again.
That's pretty elegant, eh? You can get this right. So you topologize in one way and then you quantize in the other way. So you topologize from computation to programming that. What?
It's more like you're seeing the computation as happening in some space, and that's where the homotopy part comes in.
Interesting. Rosetta Stone. Wow. That's cool.
I am a big fan of Rosetta Stones.
That's pretty cool. Okay, so test case 1, 0 multiplication. 0 times c. So what do we have to do here? 0. Oh, 0. Which is empty. Okay, how do I, because I can't see the evals here now, which is kind of the issue.
I'm just hiding div. Okay, you can't see what the. Oh. Look like this. In fact, I think if you do. I think that overloads the numerals very possibly.
Whoa.
Oh, extra private. What is one interpreted? Yeah, it is. There.
Yeah, so you're basically evaling to truths.
Yeah.
That is your test.
The symbols 0 and 1 have actually been overloaded automatically by the instance as I defined in 71 and 72, where I say 0 is identified with an empty hash map and 1 is a not so empty hash map, where the coefficient or power is 0 and the coefficient is just 1, of course.
Right.
You actually get rid of that.
So will these tests
If
still
you
work
use the
then
plus.
with this 0? Should still work.
If you hover your cursor over the info view, you'll see that 0 and 1 and such have the types of Levi-Civita.
Yeah, got it. Okay.
And if you look at the printed representation, it corresponds to what it should be. As, yeah.
Yeah. I can't see the printed stuff there.
Next time we'll run it from my screen so that we can see the info view. That I still haven't figured out who would I even ask about fixing this. The VS Code team, Lean team.
No, no. It's
More
just,
likely VS Code.
Yeah, well, it's just because some of the extensions don't work for the web version, so it's probably pretty much extensions that need like some low level stuff that can't be run in JavaScript, I guess. But we could run it straight from our VS Code if you maybe decide to just have like a less intense extension environment. Have like a minimal extensions scenario, then we can just do it direct on VS Code. You do using Apple, right? Mac.
Yeah, I use Mac.
Yeah. So you could try to keep it simple and like separate the environments. You could try to just code in a Docker container. So you can actually open VS Code in the environment of the container itself. And you can just have like a clean environment there potentially. I'm not sure if the extensions just come from. I wonder how the extensions work in that scenario. Anyway, might be worth checking out. A lot of people
I
have
asked Lean. Yeah.
a lot of people have just given up on managing virtual environments now and just literally use Docker containers for everything. It's kind of neat. What did you ask, Lean?
Parser. And I wrote it. I asked GPT rather to write a function to parse expressions. So like 1 plus h would get parsed into the appropriate hash map, so we can stop doing all this like .mk, a constructor. Let's see, what is this parser actually doing? Well, it's parsing a number, then a plus sign, 1 minus h. Not so good. Oh, here. Let numeral equal natlit, which doesn't exist, but is supposed to be some natural number literal. Right.
Oh, okay.
Number is multiple digits. I think this is supposed to be lean parse.dstring. Actually, this as useful this was not the original goal. The one I wanted to do before I have to go for dinner is to implement inf. Oh, you're still doing this.
Yeah, so if the power already exists, then it could override it. So it needs to be added to the coefficients. Apparently. Does that make any sense? Like on this line over here, on this line over here, basically. So if it already exists in the out, then it could override.
Like, what's a test case that the previous approach would give something false for?
That is where you have a multiplied by b, with a being a hash map of 1, 2, and then b being a 1, 3. So the resulting coefficients are, you're trying to find a 2, and then it should give some 6.
I think the order might be messing with you of the power and then the coefficient. So I just have a strong sense.
Oh, okay, let me output this code, and then you can tell me
yeah, to think about it too.
If it's not right. So basically it's saying that is the correct way to do it. And then the wording they use here is the following. So it says, when you calculate power prime is power 1 plus 2, there's a chance that this power already exists in the output hash map out. In such a case, you would you should add coefficient to the existing coefficient instead of overriding it. You should add coefficient prime to existing coefficient power prime instead of overriding it. So the test that it gave would be, let A have a coefficient of 2 at power 1 and B have a coefficient of 3 at power 1. When multiplied, the resulting Levi-Civita instance should have a coefficient of 6 at power 2, since 2 times 3 is 6.
Are you typing this somewhere?
This was the first test I put in, but I think I edited it. Let me do this. So if you go to test case 0, that's the other test case 0.
I'm just thinking I'm still stuck on this inversion. It just keeps looping through my head. The 1 over 1 minus x has Taylor's series 1 plus x squared and so on. But I think that's only if x's absolute value is less than 1. Thinking, what is the case if it's not? The formal expression looks like it should work, but it just seems very confusing. But I think the inverse of a negative infinite number would be some negative infinitesimal. And not 1 plus h squared, which is positive and also only growing. This seems wrong.
Or is this implementation here is wrong? Or just saying
No, of inverse. The next function is what's really like eating me.
Sorry.
Even more than the multiplication. Because the multiplication, like the issues with it I can see pretty clearly. Okay. And there's only like 2 options, both of which can be tested quickly. This one though has just captivated my attention. Defining inverse properly. What's that one called? That's not a geometric series, 1 over 1 minus x.
Okay, let's see what ChatGPT can do for us on inverse. Okay, first of all, it says it's a more complex task than implementing additional multiplication. The inverse of an element in a field is defined such that when it is multiplied by the original element, the result is the multiplicative identity. Of the field, usually denoted as 1. So in Levi-Civita numbers, this involves finding a series that when multiplied with the original number results in a series that converges to the multiplicative identity. Challenges and considerations. Convergence. The most challenging part of implementing an inverse operation in Levi-Civita numbers is ensuring convergence of the series. The Levi-Civita field isn't as straightforward as real rational numbers when it comes to inversion, especially for series with an infinite number of terms.
Yeah, that I already know. Just what can I do about it? Not every term will have an inversely computed, because there could be some, it's not like a user can actually form a number, at least not by hand, that has an infinite number of terms. Even infinite number of terms is not so bad because I can just cut it off if they were infinitesimal, but that's the problem. But in
So-
general, I don't think they have to be.
So it says implementation complexity. Given the complexity of full implementation might be beyond the scope of a simple response, it involves deep mathematical considerations, and potentially sophisticated algorithms. And you need to handle special cases like the inverse of 0, which is undefined, and the inverse of the multiplicative identity, which should return the
Is
identity.
itself, yeah. All those are encoded in that giant block of sorries. Whole litany of proofs. Like, how many lines are there for proof? And
Okay, so it's saying that here is a starting point. Where should I put it? I'll put it here.
16 things to prove.
So this is what it gave as a starting point. It says let's consider
If it's
a
empty,
case where the number is a monomial. The inverse of a monomial
well, that's so unhelpful.
would be 1.
A monomial is a pure term. It's better than nothing, but
Assuming a
not
is
great.
non-zero, there's a basic framework for this. Extending the general case. Okay, so then you develop an algorithm to compute the inverse series. Ensure that this series converges to the multiplicative identity in the field. Implement checks and balances for edge cases and ensure mathematical correctness. Testing and validation. Once you have an implementation, even if partial, it's crucial to test it thoroughly. Start with simple cases, like the inverse of a monomial.
Wait a minute. I'm going to the Wikipedia page for the Levi-Civita field. If you just type Levi-Civita, you'll always end up getting the physics thing.
It says, in order to get this right, it says, depending on your requirements, you may need to consult more specialized mathematical resources or collaborate with experts in the field. It requires advanced.
Well, I'm interviewing Sam Sanders next week, and he is an expert. That's for sure. So already there, man. Not exactly hard, given the number of experts is depressingly small.
Okay.
But growing. Mostly by people in differential equations initially, because I think the formulas and towers just got too ugly. And at some point, at least some people, including Tao, for some of their papers, it was just too messy, and they decided to finally make a switch, at least for this one paper. I don't think it'll find its appeal to other mathematicians because they're the ones who are most capable of doing analysis to begin with, which is why they're mathematicians. Well, at least half of them. The other half maybe would be more sold, the algebraists, who don't like to prove A equals B by A is less than or equal to B, B is less than or equal to A, therefore A equals B. Instead, you use an equivalence relation that they're infinitely close. And equalities are nicer to work with than inequalities. More satisfying to chain together. Definition of the field operations. Okay. The product is, yeah, whatever. That doesn't define division, though. Funny you mention expert, because 3 minutes ago, one of them emailed me because I asked him what he did during Sabbath, or Shabbos. Mikhail Katz. Great guy. What was I going to search? All right.
A lot of sorries. Let me ask what's easy ones to implement.
Yeah.
Is it because Lean is kind of like this formal theorem proving software? If we do this Hyperreal thing here, like we get the code, then it should be easy for them to implement into MATLAB, because it basically is like you can guarantee that it's correct, right? Or do you still like?
When it's actually used, it's not going to be correct because, like, ideal mathematical properties, for example, with the rational numbers, adding any two positive rationals should give you something bigger. But on real computer hardware, there's going to be an overflow at some point, so that's not actually true. This isn't like an insurmountable barrier, but it's not as simple as just like bolting them on together. Not yet, anyway.
I see.
If it was, this would be been done a long time ago.
Okay. Okay, so it's saying negation is an easy one.
Negation's already done, I think.
Why is it saying that negation? Zero related operations is the next one. And zero mole. Zero mole here. Mole 1 is also easy. Wait, do you have mole 1? Yeah. Additive, inverse, add left neg is also easy.
They're all missing. I define inverse inlines. Okay,
Okay, let's do zero mole. You prefer mole 0 to zero mole, right?
I think mole 0 and 0 mole are almost the same statement, just whether you multiply on the left or the right by 0. Hence, like left distributive, right distributive. The reason it's broken up so finely is one, because it's easier to prove them separately, and two, in case you don't need extra assumptions.
Okay. So you got both. Okay.
If anyone can make type class based programming work, it's mathematicians, because I can't imagine anyone else with more of a flair for cataloging things or classifying. Mathematician's favorite word.
This is just a schematic representation. What the hell? So Is it correct? What is a schematic representation? Yeah, so it depends on how the multiplication 0 are defined. Yes.
I added a couple things to the dependencies, including one that's ASOP, automated extensive search for obvious proofs, and also lean copilot, which will suggest some tactics for the proof's sake.
Oh, cool.
I have to first import it though. Like, okay.
This was supposed to be 0 mol, not mol 0. Got the wrong way around.
I'm working on an inverse with 10. Let me get my iPad fixed so people can see what I'm drawing. It's the 1 over 1 minus x, the 1 plus x squared, and so on. Let's see if I just cut it off at x squared. Then what? Okay, didn't work. Oh, I can also see what Julia does in symbolics.jl. Maybe I'll just have to tag it with an attribute or a new type that just says that it's supposed to have inversion performed on it, and then deal with it more symbolically. Mm. You still hear me?
Yeah, I'm trying to
Okay, yeah.
read this
Oh,
and
I
then
see.
get it done at the same
Or,
time. So enter A, apply, and simplify mol 1 hash map empty insert again. Seems right. So this Levi-Civita is already there from MATLAB, right?
No, I'm defining it,
Oh, you define it.
which is really one part defining polynomials and one part defining Levi-Civita. It's more defining the rules of polynomial manipulation. Actually,
Okay.
formal power series probably are, and actually almost definitely are in MathLib. What do they do for those? Yeah, it's in the basic for the ring theory file.
Okay.
Their whole power set thing is also uncomputable. Ugh. They, okay, it looks like inversion really is not that trivial. Maybe instead of implementing a field, be content for today with a ring, which we do have. A ring has addition and multiplication, which we did do. Oh, it also has subtraction, but that one came for free with negation.
There's a ring as a subset of a field.
Other way around.
Can you
A
explain to
field has
me?
more structure, so yeah.
Can you just explain to me nicely what a ring is? Because I was trying to learn about it today, but it wasn't that clear to me.
Well, there's this whole list of algebraic structures, and usually the way they're defined is you start with a group, which is just some set that has an operation called multiplication that behaves formally like the properties of multiplication of just whole numbers.
Yeah.
And then you can add more operations and properties of those operations to get all the way up to fields. But usually it's easier to think about it like this, to start with a field, which is because you have examples of them. The main example are the real numbers and rational numbers. Rational numbers are the computer friendly example.
Yeah.
Because adding rationals is always rational, division, multiplication, and they're commutative.
Yeah.
The ring is when you remove the ability to do division and the commutativity of it.
Okay.
Like, a good example of a ring would be a ring of n by n matrices. You can add them and you can subtract them and you can multiply them, but you may, depending on the matrix, if it's not invertible, well, you can't divide them.
Yeah. Yeah. Okay.
You can turn a ring into a field in a specific way if it has a specific property, the zero product property, that the only way to get zero through multiplication is that one of the terms must have been zero to begin with. That you cannot multiply not zero things and get zero. That's the zero product property. The matrices do not have that. You can have two matrices that are not zero, but multiplied together give zero.
You can have two matrices that are not zero but multiplied
That,
together are zero. Yeah. Yeah.
yeah, all zero entries.
Yeah. That makes sense. So what would that be called?
Wait, what would it be called?
Yeah. I mean, like, what is that property? Would that be?
Zero product property, or having no zero divisors. Zero divisor is the term for one of those terms that acts like it divides zero because you can multiply to get zero from it, though it's not zero.
Okay. Okay.
I think the try this 2 by 2 matrix, try squaring it, going from left to right, top to bottom, 0, 1, 1, 1. So 0 in the top left and then all ones. Multiply it by itself. Maybe it's missing a 0.
Are you drawing this somewhere?
No, I'm saying like write it out and
In my
multiply the
head.
matrix. Here, I'll do it by hand. 1, 1. Maybe that wasn't that word.
So are matrices rings?
Yes.
Hmm.
Yeah,
What?
one for each, or one ring for each n. The simplest example of a ring, probably the integers. There's finite examples like the numbers. Oh, okay, that's a good way to get into it. If you take the integers mod some n, the clock
Yeah.
arithmetic, if n is not prime, you'll have a ring, but you won't have a field ever. It must be, it must, whenever n is a power of a prime, not exactly just prime, a pure prime power, like a power of 2 or a power of 3 is allowed as well, then you'll have a field.
Hmm.
And never otherwise in the finite case. The only finite fields are like of this form of prime powers.
Okay.
But yeah, there's loads of rings. Integers are the simplest ring though. And going from the integers to the rationals is called the field of fractions. And it's a generic construction you can do. Because you can get the integers from the naturals by forgetting for a moment you're talking about numbers at all. And just imagine an integer as a bunch of pairs of numbers, all of which have the same difference, which is the integer they're supposed to encode. But there are infinitely many pairs that can represent it, so they're all identified together. And this is called a quotient. Maybe Urs mentioned this in his talk somewhere, the word quotient, probably thrown out too freely.
Maybe once or twice.
Whatever. Point is, you can go from a ring without zero divisors to a field, and the generic construction that does so is called the field of fractions, because the standard example is going from the integers to the rationals.
Oh, well,
Also,
OBS disconnected. No, reconnected. Let's check if OBS is still going.
I think now is a good time to stop, though. It's 8:30 here, and it's almost midnight for you, and I need to eat.
Okay, so let's see. How did we do here? So we got a couple hours.
Mole, and I got a
let's
decent
see.
portion of what I got was not code, but realizing that inverse is not as simple as hoped. The implementation for a monomial is trivial. You don't even need a for loop.
Okay, well, that was a good sesh. I'm gonna hit the stop.
Yeah. Oh, wait, before you do that, I'm just going to make a git commit, then you can go.
All right, cool.